Hi, in this video, we're going to take a look at multiple linear regression. All right, what is multiple linear regression? I'm in a situation where I have data, I have one variable that I want to know more about, or I want to predict, or I want to control, and I have multiple, more than one, predictor variables that I want to use to model as inputs or independent variables relative to that target variable. All right, and so it's multiple linear regression. And that what we're going to do is we're going to create the simplest mathematical equation we can for my target variable y and all of my predictor variables, which we'll call some kind of x. Okay, now linear regression, we're going to do straight line equations in a higher dimensional sense. These are the simplest equations we possibly can. There are tons and tons of other types of statistical models that I could use, but linear regression is mathematically the simplest. And frankly, if you're going to be doing something like machine learning, you should learn linear regression first before you go on to the more advanced models. Why is that? Well, linear regression is simpler, it's easier to understand, it's easier to interpret, and if you do things right for a linear regression model, you're going to just inherently be doing things right for neural networks, tree models, all the other types of stochastic gradient boosting, or k nearest neighbors, any other type of modeling that you're using. Good data prep for linear regression is good data prep for machine learning. So we always want to be proficient at linear regression if we're going to be doing something like predictive analytics or machine learning with more advanced models. Now here, we're taking the point of view of the statistician. The statistician, we want to interpret our models. Now we could also use it for prediction. That's definitely a good way to go, but the interpretation is more important to a statistician. Yeah, so let's dig into it. So multiple linear regression is a statistical technique that uses explanatory variables, I call them predictor variables, to predict the outcome of the response variable. The goal of multiple linear regression is to model the relationship between the explanatory and the response variable. All right. This generalizes simple linear regression, which considers only one explanatory variable. So here's our equation for multiple linear regression. I've got my target variable. I have my intercept term. Notice that there's no variable next to it. There's no x, there's no y. Then for each of these x's, these are different predictor variables, explanatory variables I have, and then I have a coefficient. And so if you look at this for a moment, you'll realize that if I have all these x variables in my model, and I have a y variable being modeled, this is mathematically the simplest thing I could possibly do. Right. Now over here, we have a little epsilon that accounts for the randomness in the system that's going on, that accounts for all variables that should be included that are not, or some other aspects, some other shortcomings in our model. All right, so y is our dependent variable. All the x's are independent variables. All those betas are parameters. Beta 0 is the intercept. So if I plugged in 0 for all of my predictor variable values, I would get the intercept. And all the other betas are coefficients of the predictor variables. And so if I change a variable by 1, then the corresponding coefficient tells me how much on average do I expect my target variable to change. And that's when I say that increase by 1, we're assuming that all the other variables stay the same. Now, epsilon is our error term. This captures all shortcomings of our model. Maybe I'm missing a variable. Maybe the model structure isn't quite right. The epsilon captures everything else. There's also random fluctuations that just can't be accounted for. Anything like that, we basically just dump it all into the epsilon term. And we also call this the residual term. And this represents the difference between the observed and the predicted values of y. And normally, most of the time, we're going to assume that the error is normally distributed with a mean of 0. And we're going to talk about these assumptions a lot. The parameters of the model are often estimated using least squares method. So here, what we're going to do, least squares method, we're going to minimize the sum of the squared residuals, and we'll represent this in this manner. So mathematically, we're not going to actually execute this. We're going to drop this into R, Python, SAS, whatever. We're going to put it into the system, and we're going to let the computer figure this out. But to make sure we understand what's going on, we're going to talk about it. All right, so here, you'll notice that this is the same as the equation I had above, but there's no epsilon. There's no error terms. So what this is this is the modeled value for y using my data. So here, remember, the epsilon has a mean of 0. Epsilon has a mean of 0. So what we're doing is I'm saying, hey, I'm going to take the value that I get from my model when the error is at its average. That's the modeled value here. So that's my predicted value. I take the difference with the true observed value that we have in our data, do subtraction. All right, so the difference is an indication of how far off my model is. Models will always have some error going on in real life situations. There's always a difference between model and observed value in all meaningful situations. So here is the difference between my data, which I treat as being 100% true and correct, and the modeled value. Okay, now I've got plus or minus depending on if the model was high or low. And so then I want to get a cumulative aspect to how good my model is. So what I'm going to do, I have plus or minuses. If I go through and start adding up all those plus or minuses, they're going to cancel out to 0. So instead of just adding them up straight, we're going to square this bad boy so that they're all positive. Okay, so now here, these are all positive terms in the summation. Then I'm going to add them all up. I take the difference between data and modeled value, square it, add them all up. All right, so that is the error, cumulatively, the sum of the squared error of my model. Now, what we're going to do when I'm fitting the model, I'm going to look at these betas, and I'm going to set the beta values here to set up so that we get the smallest summation I can possibly get mathematically. And so this is approaching things kind of like from a calculus point of view. I'm going to minimize what's going on. All right, so there are some assumptions in multiple linear regression, and it's rather important that we get these right when we do a linear regression model. First one, linearity. This assumption is saying that I have this XY equation right, that the structure of the equation is the right equation to be using. I shouldn't be using some other form of mathematical relationship. Next one is that we have independence between the residuals. Now, this is kind of interesting. This is different from anything we've talked about in this video series I've been working on. That the residuals are independent, but we're making the point of view that y is not independent of x. Previously, we've always said like independence, independence, independence. Now, I've got a whole bag of variables going on, and I'm saying that only the residuals are independent. The x's, maybe, maybe not. Y and x, definitely not. Now, the next one is homoscedasticity, and we're going to say that the residuals have constant variance. Now, the next one, now this one we need for hypothesis testing and other things. We actually don't need this for fitting the model, but we do need that mean 0, but we don't actually need normally distributed for the purpose of just fitting the equation. But if I want to do hypothesis testing, I need normality of the residuals. All right, so we want the residuals to be normally distributed. So normally distributed, mean 0, and constant variance here. Now, when we say constant variance, that's with respect to x. If I change the x values, the variance of the residuals does not change. And this next one, this is the first time we've really talked about this, is no multicollinearity. Okay, So imagine the situation that I've got two predictor variables, and those two predictor variables have nearly perfect correlation. They have nearly perfect correlation. Okay, well, if I put both of them in my model, they're redundant with each other. And what's going to end up happening when they're redundant with each other is it's going to actually, it would be better if I got rid of one and had it. So imagine like you're talking about a sports team and I have two-star running backs. When you have two-star athletes in the same position, the coach can have problems because they've got two really great talents right there. They want to use both of them, but they're always at odds with each other because there's only so much game time to go around. And so they both want to be star athletes. The other one has to get out of the way. There's conflict, there's problems. And so what, this is similar in statistics in that if I've got two variables that are super correlated close to each other, then there's a redundancy. And really, I only want one for simplicity. Now, which one do I use? Well, one will be a little bit better in terms of a predictor variable for y, and it's probably the one I want to use. Now, when I say multi-collinearity, the situation get far more complicated when we start talking about multi-collinearity, because in that situation, it might be that if I take three variables, so imagine if I take any two, I can get the third one nearly perfectly in terms of like a correlation aspect. We'll talk about how to measure this in a little bit. But if I take any two, I can get the third. Well, that means in that situation, I want 2 out of 3. And the next question will be like, which two do I pick? That's a very good question. This is something to be worried about. And there's no solid, complete, good answer for that. We have to just work through all of the output from R and figure out what's best. There are algorithms for just doing it automatically. It's better if you do it step by step, paying attention to it. But if I've got thousands and thousands of predictor variables, which sometimes you do have over 1,000 predictor variables when you're working on a project, that multi-collinearity gets a lot more complicated because it could be, like it's a combination of 100 variables ends up being multi-collinear. So in practice, these assumptions are checked after fitting the model. So I fit my model, then I take a look and confirm that these are solid on there. And if they're violated, the results may not be reliable. Additionally, to assess the goodness of fit of the model, we usually look at the R-squared statistic, which represents the proportion of variance in the dependent variable that is explained by the independent variables we are using to model the dependent variable. All right, so now let's talk about interpreting multiple linear regression models. So when we interpret the results from a multiple linear regression analysis, first thing we're going to want to do is understand the coefficients. All right, so for the coefficients, these represent the change in the dependent variable for 1 unit change in the independent variable, the corresponding independent variable, assuming all the others are held constants. So beta 1 is the expected change, the on average change of y for 1 unit change in x1 when all the other independent variables are constants. The intercept is the expected value of y when all independent variables are equal to 0. Now, it's pretty standard that when I run multiple linear regression, our statistics software will give us a p-value associated with each coefficient. Typically, this is going to be testing the null hypothesis that that coefficient is equal to 0, no effect. If we have a small p-value, typically less than 0.05, this indicates that we can reject the null hypothesis. Now, my personal experience is that you don't want, like, if I have a bunch of predictor variables, I'll be looking to trim out ones that are not useful. Going off of p-values, it's okay to have a few non-statistically significant p-values. That's my experience off of building models and trying to fit different models and seeing what works out. So usually, if I only have a few predictors, I'll keep one If I have a larger set of predictor variables, I might have 1, 2, or 3 non-statistically significant coefficients. I'm not going to get too deep into feature selection in this video, but you don't have to make sure everything's statistically significant. Another important statistic is our R-squared value. This is a number between 0 and 1. Notice that we have a square on that indicating that it's always 0 or positive. It's between 0 and 1 and represents the proportion of variance in the dependent variable that is explained by the independent variable. How do we get this? Well, what I do is I take sum of squares regression, divide by sum of squares total, and do 1 minus that fraction. That's our R-squared. So SS res is the residual sum of squares. That's that sum of squares error. Sum of squares total is y minus y bar squared. Add it all up. And that's the total sum of squares. A higher R squared indicates a better fit of the model. Now, there's a caveat on that. It works out mathematically. If I keep on throwing in random noise variables, if I keep on putting in more and more variables, R squared can only increase. 100% guaranteed. All right. So because of that, R squared is not the best way to go if there's a risk of overfitting. When I say overfitting, I mean I have too many predictor variables, or I have a redundancy in predictor variables. So one thing I want to do is I only trust R squared when I know I don't have any excess predictor variables floating around in my model. Finally, after fitting a multiple linear regression model, it's important to check the assumptions of the model. So remember that those assumptions are linearity, independence on the residuals, constant variance of the residuals with respect to predictor variables, normality, and no multicollinearity. Various diagnostic plots and tests can be used to check these assumptions. If these assumptions are seriously violated, the results of the analysis might be crap and we won't know it. In these cases, the model may need to be revised, for instance, by maybe transforming the variables, removing outliers, or considering a different model structure, or trying to get another predictor variable to include. All right, now let's talk about fitting a multiple linear regression model. So the key to this is that we want to minimize the sum of the squared errors. That's it. That's the whole big idea. And so if you've taken Calc 1, you've spent a lot of time trying to minimize or maximize things, mathematically. Well, statisticians have sat down, they've done the calculus, they've worked out the math for you. You don't need to worry about it. You just need to have an idea of what's going on. And so the residuals, which are represented by epsilon in our model structure, are the difference between the observed and the predicted values. And so when I have a given set of values, so let's say that I have a data record here that I have, for one particular record, I have the x1, the x2, the x3, all the way up to xp, and I have the target variable that I'm interested in. I have estimated values of my coefficients. So here, and these are found by minimizing that sum of squares. This difference here is the error of my model for that particular record. And we'll have, n observations is how we denote it. The least squares method minimizes the sum of squared errors. So I square the error and then add them all up. And we get that by doing exactly what I talked about previously. Subtract y from the model values, square that bad boy, then add them all up. To find the values of betas that minimize this, we can use partial derivatives of sum of squares residuals with respect to each individual beta and set them equal to 0. I'm doing basic calculus. These are called the normal equations. Solving these equations give the least squares estimate of the parameters. If you go to my YouTube playlist on linear models, I go through like the theory 100% completely on this aspect. Everything in the videos are handwritten, not really great, but that's what I had available to me during COVID. You can go knee deep and upside down, and the theory is awesome. Now, in that approach, if you watch those videos, I do everything using matrices to make this simpler. If I've got 10 different variables for predicting and I have a target variable, I've got a good number of variables going on. I don't want to manually have each individual equation. We can work this out using matrix notation. And so here's what we're going to do is that I have X transpose X. So this X is the matrix where each column corresponds to a predictor variable. Each row corresponds to a record that I have. All right. And so then the equation for beta hat is that beta hat times this product needs to equal X transpose times Y. All right. And so now, if I use matrix inverse, we can get a formula for beta hat. Something that's interesting to know is that this formula here is what we do in theory. It works out nice. It works out great. But R, SAS, JUMP, whatever you're using, does not use this equation. This equation has problems with it. And so when I actually give it real life data, this is not how the computer is going to compute it. It's going to use a more advanced technique. We don't care. We'll get something sufficient, something good. From our point of view, we're going to drop it into the computer and it's going to go. And so something about this is that this has to be an invertible matrix. If it's not invertible, then there's problems, but R knows how to handle that. And so when it's not invertible, we have multicollinearity in our data. And the least squares estimate there is not a unique estimate that I should be using based off my data. And things get just more complicated. Problems in statistics can arise when this matrix is close but not quite not invertible. All right, so now let's talk about hypothesis testing when we're doing multiple linear regression. So there's some fundamental hypotheses that we're going to be looking at if I'm interested in doing hypothesis testing. All right, one is for the overall aspect of the model. The other ones are going to be for individual predictor variables. There's others that we get into, but those two are the fundamental ones. So I'm going to start in the opposite order that I do in real life. In real life, I'm going to do ANOVA first, and I'll do individual coefficients second. Here, I'm going to switch it up. So hypothesis testing and multiple linear regression, we use this to determine the statistical significance of our parameters. That's the intercepts and the coefficients and the overall fit. And overall fit, we use ANOVA. So individual parameters, that is for coefficient and intercepts, we want to see, do I want this individual term in my model? If statistically, it looks like from a hypothesis testing point of view, if it looks like it is equal to 0, then I want to throw it out. Because if it's equal to 0, then it's not adding anything to my model. I should get rid of it. I should get a simpler model. And getting rid of predictor variables that I don't actually need or don't actually want will actually improve the overall model because we won't have that multicollinearity aspect going on. And so what we're going to do, we're going to have a null hypothesis that, and we do this for every single predictor variable I have. If I have 20 predictor variables, I'm doing this 20 times. For each individual predictor variable, I run a hypothesis test. Is the coefficient equal to 0? If it's equal to 0, I want to kick it out. And so if it's equal to 0, that means that it has no significant effect on the response variable. The alternative hypothesis is that the coefficient is not equal to 0. And so that means I want to keep it in there. And so here's our test statistic. So we have our estimated value minus 0. This is very similar to regular hypothesis testing, divided by the standard error of my estimate. Now, I'm not giving you the actual standard error here. Why? Because we've got two different situations. we have the intercept, and we have predictor coefficients. They actually have different standard error formulas. And so conceptually for hypothesis testing, for the purpose of this video, we don't care what the difference is. We're just running it, and we'll let R, jump, SAS, whatever you're using, just figure that out for us. All right, so if all of the assumptions that I listed out previously are correct, and there's a lot there, if all of them are correct, then under the null hypothesis, this statistic here follows a t-distribution with n minus the number of predictors minus 1 degrees of freedom. N is the number of observations, p is the number of predictor variables, and then we have a minus 1 on there. If the absolute value of the test statistic is large, or equivalent, the p-value is small, we reject the null hypothesis and conclude that the predictor variable is statistically significant, which means I want to keep it in my model. This test can be applied to both the coefficients and the intercept. For the intercept, the null hypothesis is that the intercept is equal to 0, which would mean I would want no intercept in my model. And the alternative hypothesis is that the intercept does not equal 0. If the intercept is not statistically significant, this does not mean that the model has no predictive value. It only means that the expected value of the response variable is 0 when all other predictors are 0. Typically, most of the time, statisticians don't even look at the intercept for hypothesis testing. We just assume that it's correct, it should be there, keep it there. When I've had problems with overfitting, I have chosen to remove the intercept in my professional work when I was in a situation that my clientele wanted all the predictor variables in there, and it ended up that having the intercept was combined with all the other variables gave me multicollinearity. That was a good day when I figured that out, because the clientele absolutely wanted all the predictor variables in. They didn't want anything cut out, but I was clearly seeing multicollinearity. And the intercept corresponds to a predictor variable of all constant ones. And I had multicollinearity, kicked it out, boom, I had a much better model, and my clientele didn't know the difference one way or another. Now, here is the hypothesis test that I actually start with. This is the one that you should do first, in my opinion, but this is for overall, so it's a little bit more complicated. What we're going to do, we're going to run ANOVA, and my goal is to check, is there something good in my model? Do I have one or more good predictor variables? Now, when I do this, after I reject the null hypothesis and conclude that there is something good in my model, what I'm concluding, let's say I have 10 predictor variables. If I reject the null hypothesis and go with the alternative on my ANOVA, let's say there are 10 predictor variables. When I reject the null hypothesis, I conclude one or more of my predictor variables are informative. If I have 10 variables, that could be exactly one is good, I don't know which one, or all 10, or 5 of them, 2 of them, 3 of them, I don't know. I just know one or more are good. After that, I'm gonna go up to that coefficient hypothesis testing and check to see which ones look like they're useful. All right, so for ANOVA, we're going to use an F test to check the overall significance of the regression model. This is done using ANOVA, of course, and the null hypothesis is that every single regression coefficient except the intercept is equal to 0, and the alternative hypothesis is that at least one, that is one or more coefficients, do not equal 0. Null hypothesis, all of them are equal to 0. Alternative, at least one is not. My test statistic is going to be my sum of squares regression divided by p, divided by sum of squares error divided by n minus p minus 1. Remember, this is an F test, so this is a ratio of variances. So SSR is the sum of squares due to regression. This is the amount of variance in my target variable that's explained by the model. SSE is the sum of squares due to error. This is what's not explained by my model. N is the number of observations, P is the number of predictors. And under all of the assumptions, so if every single assumption I talked about earlier is correct and true, then this F follows an F distribution with P and N minus P minus 1 degrees of freedom. That means I can do hypothesis testing on this bad boy. Now, for us, most of the time, whatever statistics software we're running is just going to spit all this out. And it's our job to look at it and interpret, make sure we understand what's going on. All right, so now let's talk about the residuals in multiple linear regression. We're getting down to the errors. All right, so in multiple linear regression, the residuals, or our error terms, represent the difference between our observed data, our observed target variable, and the modeled predicted values. And the distribution of the residuals play a vital role in validating the assumptions of our model. Our key assumptions about residuals are that we have independence between the residuals. So there's no like autoregressive or anything like that going on. We have constant variance of our residuals. And when I say constant, if I change the X values, the variance of the residuals does not change. And then normality, in that we're saying that the residuals are independent, identically distributed, normally distributed, so they all have zero mean and they all have the same variance value. And so here we write it this way. Our errors are normally distributed with mean 0 and constant variance with respect to X. All right, so now how do we check our assumptions? So we're going to do this after my model is built, after I've done the computations. First and foremost, we're going to look at residuals versus fitted values. Okay, so if I've got 10 predictor variables, it's going to be complicated for me to have, to start incorporating each individual predictor variable in the residuals. We can, that's one way to check things, but typically the one that's most important for us in multiple linear regression is to do a scatter plot of residuals on the y coordinates, fitted value on the x coordinates. This plot helps to check the assumptions of linearity and homoscedasticity. Ideally, the plot should show no clear pattern, and the points should be symmetrically distributed about the horizontal axis. Next one that we want to use is a normal QQ plot. So what we're going to do, we want to check, are my residuals normally distributed? The residuals are plotted against the expected value for the normal distribution. If the residuals are normally distributed, the points should roughly follow a 45-degree reference line. Now, in the middle, typically, it's going to be pretty tight. It's how much of a degree do the points deviate from the line far to the left, far to the right. It's going to be what's important. Next one is the scale location plot. This is another plot used to check the assumptions of homoscedasticity. The square roots of the absolute residuals are plotted against the fitted value. Again, we should see no clear pattern in the plot. And so this is similar to residual versus fitted plot, but instead I take absolute value and square root it. And then residuals versus leverage. So it's going to work out that mathematically different records, different rows of data are going to have more or less influence on the model than other records. Okay, so in that situation, I'm going to look at my residuals versus the leverage to see if there might be something going on. Because what can happen is that if I have like one huge leverage observation, it can pull the rest of the model over to that one value and throw off the whole thing. And that's an indication I should have thrown out that value before I fit my model. All right, so we want to evaluate our model after it's built. And so what we're going to do, first and foremost, we're going to do that residual analysis. And so I'm going to look at the residuals. We're going to be looking at a lot of plots. Plots are big on this one. We're going to check normality of our residuals. And we can do this using histograms or QQ plots. If the residuals are not normally distributed, this may indicate that I really don't have a good model structure, or possibly I've got like variables that I need to like go and find, get more data, maybe do a transformation. There's a lot of different situations that could be it. Homoscedasticity, we can have that the variance of the residuals aren't constant for different levels of the fitted values. This can be checked visually using a plot of the residuals versus fitted values. If I see a clear pattern, frequently a funnel shape can come up. It may suggest that the model's variance is not constant, it's heteroscedastic, and the model may need some adjusting. Typically, in that situation, we're going to do a transformation on our target variable. We can also do transformations on our predictors. And then the next one is independence. The residuals should be independent of each other. This can be checked by plotting residuals against time. I should not see an autoregressive pattern. And so what I'm going to do, I'm going to say, if there was a time order to my data coming in, first observation, second observation, third, and so on, I'll plot residual on the y-axis, time on the x-axis, and if it looks like I have autoregression, if I have a pattern, then that indicates that there's a problem and I need to address it. The next way that we're going to evaluate our model is R squared. And so here, this represents the proportion of variance that our model accounts for on our dependent variable. And so this is equal to sum of squares of error divided by sum of squares total, and then I subtract that ratio from 1. Now, there's a problem with R squared. If I have excessive predictor variables, or I have predictor variables that should not be there, my R squared can look a lot better than it really is. That just by flukes in the data, my R squared looks really, really good, but in reality, my model has problems because I have junk variables in there. Okay, so something that we can do to protect ourselves from this is to just kind of put a little tweak on our R squared. What we're going to do, I'm going to take this formula, but instead of having sum of squares error here, I'm going to take sum of squares error divided by n minus p minus 1. Instead of having sum of squares total here, I'm going to go sum of squares total divided by n minus 1. Now, if I look at this, I'll notice that this fraction here is always greater than this fraction here. If I, divide by fraction, same as multiplying by the reciprocal, I'll notice that this is in the denominator. If I make this into just one fraction, this is on the top. N minus 1 is greater than n minus p minus 1. So that means I'm multiplying by something greater than 1. This has to be greater than this here. So my adjusted R squared after I do the minus, adjusted R squared has to be less than R squared. Now, this is important because this is taking into account the number of predictors I have. So this is the R squared that I trust a lot more. Specifically, if you see a difference between R squared and adjusted R squared, that is an indication that you have overfit your model. Pump those brakes. You know you need to do something with removing some junk variables. Now, the F statistic from that ANOVA test is another way to check to see, do we have a good model? So, there's some things. So here, the F test and the T test are being brought in, and really in two different possible ways for checking model quality, but also possible for inference on hypothesis testing, depending on the point of view of what's important to you. And so one thing we want to see for our coefficients is we would like to see that all of the p-values are statistically significant, less than 0.05, if that's possible. I've been in a situation where higher dimensional variables, we can't always get all of them down, but it's not a big deal as long as we're not overfitting. Now, let's talk about using R to check our assumptions of multiple linear regression. What we're going to do here is I'm going to just create a random data. I'm going to create a model. And what we're going to do is we're going to look at some different ways to evaluate. So the first one I'm going to do, I'm going to plot the modeled value on the x-axis, and I'm going to put the residual on the vertical axis. And then you notice I put a horizontal line here. First and foremost, I want to see no patterns in my dots. If I see a pattern, like there's a shape or something going on, then that's an indication that there's a problem with my model, with my data. Next thing I want to see that this looks like a random cloud of dots. About half are above that horizontal line, about half are below the horizontal line, and there's no pattern, and it looks like the variance is balanced. So something that can happen is that it could potentially happen that we don't have normally distributed. Let's say I have skew right, then it might be that all the dots on the bottom are close, but just a little bit below zero, while there's more of a spread up top if my residuals are skewed right. And that would be an indication that I have violated the assumptions of multiple linear regression. I want to pump the brakes. I want to go back. I probably would need to do transformations on my variables. All right, so we want to see random scatter of dots, no clear pattern or departures from the horizontal line at zero. If the residuals fan out from the line, forming a cone shape, this is an indication that we do not have constant variance. Now, the next one we want to take a look at is the normality of our residuals. And to do that, we can do Shapiro-Wilk, we can do a histogram, we can do a QQ plot to not go too overboard on it. Here I'm doing a normal QQ plot. Typically, what's going to happen is that in the middle on QQ plot, the dots are going to be pretty tight. And we're going to check to see how much do these kind of deviate. Here, there's kind of like a range of values. What I don't want to see a hard, firm, let's say like at this point, all the dots took this hard, firm deviation from the line, either above or below the line. I don't want to see a hard, firm deviation of the dots above or below the line. Also, I have had it happen professionally where you see this little curve away from the line. I think that's fine for this particular model. Also, it's randomly generated data, so I know it's okay. But it's possible that we could get like more of a deviation here. And that's an indication that there might be deviation from normality. Usually the middle part is not such a big deal. And so ideally, everything would go right on top of that 45-degree reference line. Some statistical software will give us like like horns. They give us a range of what's reasonable. R tends to not do that because R wants you to have to like really make a judgment call on what's going on. Now, the next thing we're going to check is for independence between our residuals. All right, so honestly, we can't fully evaluate the independence, but what we can do, we can check to make sure we do not have an autoregressive aspect. Autoregressive, what I'm saying there is, let's say I have two residuals and then I have the third. It's possible that the distribution of the third is related to the distribution of the first two. So whatever values I have here, after these are hard fixed values, it might work out that the distribution of this third residual actually has a changed distribution. And so what we want to do an autoregressive plot, and we want to see, does it look like there's autoregression? For us, we don't want to see a pattern. We want it to look like just like random noise going up and down, up and down, up and down. If I see a pattern, that's an indication of a problem. So we want no clear pattern in our plot that we have here. And we don't want to see any trends. And so if we see an upward trend or a downward trend or a pattern, that could indicate that we have autocorrelation, which violates the assumption of independence. Now, next one we can talk about is Cook's distance. All right, so first thing I want to do before I talk about Cook's distance, I want to talk about the plot function in R. So when I run the plot function on a linear regression model, I just drop it in. All right, now there are actually 6 different plots that we can put in there. If I don't specify the which, what's going to happen is it's going to give me like the 4 baseline basic ones to plot out and to look at. What R is going to do on all those plots, it's going to take the three most extreme values, the three most extreme residuals, and it's going to mark those three every single time. So what's going to happen is that at times it can look like I have outliers because it marks three every single time. Let's say I have no outliers, there's nothing going on. R is still going to mark the three most extreme ones for us to easily find and point out. So here with Cook's distance, we have a good example that I've got 3 points plotted here. And this is saying that the 74th observation, 95th observation, and the 97th observation all have larger Cook's distance than the rest. It always takes the most extreme three. Here, I probably would take a look at 97, but these other two, I would go ahead and leave alone. Remember, you will always have three largest. If I have any data set, I will always have a largest value, and I will have a smallest value. And so no matter what I'm doing, I will always have three largest values in there. Now, how do I get the other plots in here? What I can do, I can set which equals 1, 2, 3, 4, 5, 6, and R will print all 6 of those plots. Now, to run hypothesis testing in R, we're going to use the summary function or maybe the ANOVA function. Summary does both of them, so that's the one that I prefer. So I've got my model. If I run summary on my model, what's going to end up happening is that you'll see it does a bunch of stuff for me. This is nice. This is sweet. First thing I want to point out is that it's going to run that ANOVA for me that we were talking about earlier. It's going to give me the p-value. Immediately, that tells me that from a hypothesis testing point of view, one or more predictor variables are statistically significant. It doesn't tell me which. It may be only one is informative. In that case, it doesn't tell me which one, or maybe all 10. I don't know. I have to dig deeper. It's going to give me the degrees of freedom for the F statistic. It's going to give me the R squared value and the adjusted R squared value. Notice that these are close to each other. If these are far apart, that's an indication of overfitting. Here is the residual standard error. So this is, that constant variance evaluation, constant standard error instead of variance. So, just take a square root. And then here, this is telling me what is the formula of my model. Here is the distribution of my residuals. In linear regression, our residuals always have a mean of 0 if I'm using these, minimizing the sum of squares error. Mean of 0, so it's not here. Here's the median. If this is substantially different from 0, that's an indication that I have skewness in my residuals. And here I want to see interquartile 1 and third quartile to be close to each other, but opposites in magnitude. Here they're close. And ideally, the minimum and the maximum will be close to each other, but opposite signs. Here, but I'm more tolerant of that. So here I'm looking, I want the median to be close to 0. I want first quartile, third quartile to be absolute values approximately equal to each other if we're dealing with symmetric residuals. Symmetric about 0. Oh, and I forgot to say, here we get our test statistic for the intercept and for each of our predictor variables. It does the estimated coefficient. It does, so this is the coefficient in my model, that beta hat. Here's the intercept hat. Here's the standard error here. Here's the test statistic, and here's the p-value for us. All right, well, that's all I've got for you. Life is short. Do math.